Composition of functions. Definition. Let G be a function from the set A to the set B, and let F be a function from the set B to the set C. The composition of the functions f and g, denoted for all A in set A by f composed of g, is defined by f composed of g of A is equal to f of g of A. In short, f of g applies g of A first, then that result is applied to f. And note, the composition of f composed of g cannot be defined unless the range of g is a subset of the domain of f. That's a lot of words. Next we'll take a look at an image that'll kind of show what this means and hopefully make a little more sense. In this graphic we have three circles here, set A, set B, and set C. And we have 3 points inside of each one of those circles. Element A is in set A, element G of A is in set B, and element F of G of A is in set C. Next, we'll take a look at the functions that get us from one to the other. So the function that takes A excuse me, to set B is the function G of A. That gives us element G of A in set B. After that is done, then you can take that result and apply the function f to it, and you get f of g of A. Note that is, you're taking the result of the function g of element A, taking that result and applying it to the function f. So we can draw a line directly from A to C and say this is the composition f composed of g of A. And then generally we'll just look at the function g taking us from set A to set B, and the function f taking us from set B to set C. Let's look at an example. Let G be the function from the set ABC to itself such that G of A equals B, G of B equals C, and G of C equals A. Let F be the function from the set ABC to the set 1, 2, 3, such that F of A equals 3, F of B equals 2, and F of C equals 1. What is the composition of F and G? And what is the composition of G and F? To start with, we have F composed of G of A gets rewritten to F of G of A, and then we want to substitute in G of A's value. G of A's value was B, as we saw up above, so now we have F of B. F of B, we see that value from up above is equal to 2, so that's 2. And then we've got F of G of B. Rewrite that. F of G of B. And from up above, we have G of B is equal to C, so substitute that in. We now have F of C. F of C is equal to 1. And we'll do our last one, F composed of G of C. Rewrite F of G of C, and G of C was equal to A, so this becomes F of A, and F of A is equal to 3. Then we'll look at G composed of F, and when we look at this, this is not going to be something that's definable. We'll say is not defined because the range of F is not a subset of the domain of G. They are talking about completely different kinds of things, so it's not a definable composition. Let's look at another example. Let f and g be the functions from the set of integers to the set of integers defined by f of x equals 2x plus 3 and g of x equals 3x plus 2. What is the composition f and g, and what is the composition of g and f? So let's look at the composition of f and g first. So we'll write f composed of g of x, and we'll rewrite that as f of g of x, and then we'll substitute in what g of x is equal to. So g of x is 3x plus 2, and then we'll substitute that in to what f of x is. So we go 2, and then we have the x part of f of x, so that's where we substitute in the 3x plus 2 there. So we have 2 parentheses 3x plus 2, close the parentheses, and plus 3. And then we'll simply multiply through. So we get 6x plus 4 plus 3. Simplify that a little bit, we get 6x plus 7. And then we'll do g composed of f of x, and rewrite that, g of f of x. Substitute in the value for f of x. So we get g of 2x plus 3. And then we'll substitute that into the g of x. So we get 3, 2x plus 3 inside of parentheses, plus 2. Then we'll multiply through, and we get 6x plus 9 plus 2 simplifies to 6x plus 11. And note that these compositions are not equal. The commutative property does not hold.